I would like us now to go through a couple of reminders about basic mechanisms related to operating systems. A few reminders. The operating system job is to actually mask the hardware details to the application, and it creates a very nice and clean software and hardware interface. And as such, it has three main tasks. The first one will be the multitasking management that we did talk about already. Making sure that all the tasks are running one after the other on the CPU and making sure you get enough CPU time to implement or to realize your various deadlines. But also two fundamentals operation that your OS should do. It will do some memory management, dealing with allocation, deallocation, garbage collection, and so on and so forth. In the specific context of an embedded system, you should not have to deal with that too much because, as a matter of fact, you are not going to use most of the time any dynamic allocation, so you won't have to create a mess with your memory. But the last operation that your operating system does is the I/O management. It will be able to deal with the various peripherals through drivers. Open I2C, open the file system if you have a file system, and so on and so forth. So it provides you with a very high-level access entry point from your application into the hardware module. This is not particularly done to simplify your job as a programmer. A library will do the job very nice and cleanly. But it's meant to avoid collision between various tasks on some specifically important shared resources. Let's go through multitasking in operating system. The job of your operating system, as I said, is to deal with various processes, various tasks. And it does so by dealing with the process creation, code execution, and the control of the execution, and finally the final destruction of your process when you're done. Again, most of the time in an operating system, in an embedded system, you will create some tasks and you will keep them until the system is plugged off. The operating system also needs to take care of the communication between those tasks, guaranteeing proper synchronization, avoiding deadlocks, and dealing with data exchange and guaranteeing data integrity between the tasks. So one of the fundamental jobs as the application developer is to split your application into tasks, potentially with priority levels in between those tasks. And those tasks can be considered as fully independent pieces of software. They should be encapsulated in a while-one loop, and they will be doing something very specific. Once you have that in your priorities, your scheduler can start cadencing all of those. And the scheduler will basically assign a task status to all of those tasks. You will have at least three states that commonly exist. I'm talking about a simple operating system, of course. Types of operating system that you will find in most embedded systems, like FreeRTOS, for example. So you'll have the three commonly states, which is ready. The task is ready to have some CPU time and to be executed. The task could be running. It's actually executed on the core, or it could be blocked. Blocked means that the task will be waiting for a resource or an event to be executed. For example, let's consider a task dealing with messages coming from the UART. Well, until you received a message on the UART, it would be pointless to execute the task. So the task will be blocked until you receive a message from the UART that will put them inside of the ready states, ready pools, and then being able to run when available. As you can see from the diagram at the bottom of this slide, tasks can move between the running and ready states. So for example, when the operating system decides that the task that was running had enough CPU time and need to be replaced by another ready task, it can put back this task in the ready pool and execute another task. Scheduling. The notion of scheduling consists of deciding which task to execute on the processor according to a given strategy. And as I said earlier, there are various types of strategies, various types of scheduler algorithms that exist that will be able to either guarantee an equal amount of time on all the tasks on the CPU, or that will guarantee a policy of earlier deadline first, and so on and so forth. The transition from one task to another is called context switching. When the task is running, the operating system will kick in, decide to stop this task and jump to another one. That will be switching the context between these two tasks. To some extent, it will be relatively similar to what you have seen already with interrupts, when you jump from a thread mode into the interrupt handler mode. And the job of your scheduler is to minimize the temporal overhead coming from switching from a task to another, while still guaranteeing that the tasks get processed. So if your scheduler stops the task too quickly to switch between them to get enough CPU time to all of them, you will pay a large price in this context switching. And the job of your scheduler will be to understand what needs to be operated first to minimize this overhead. One of the most known and basic scheduler approaches is the round-robin scheduling. With the round-robin scheduling, the idea is that you have time slices that are assigned to each process in an equal portion in circular order, without dealing with any priorities. If you have 5 tasks, your CPU time will be shared and split in between those 5 tasks. It is a very simple, easy to implement scheduling, and it's starvation-free. The notion of starvation is a problem that is encountered when one task cannot be executed because of other tasks are running, tasks of higher priority and whatnot. So with a round robin, because everybody has the same priority and the CPU time is shared between all those tasks, you will be able to run all your tasks without any complications, any starvation. All right, let's now go through my personal favorite, how to handle context switching. I would like to remind you the memory organization that we have seen so far in our embedded systems. At the bottom of the SRAM space, we do have our statically allocated variables, data, that are there. And then the rest of the memory is organized in between the heap growing upwards and the stack growing downwards, the stack starting at the top of our SRAM space, or at the available SRAM space. So this is good, but now the memory organization will be slightly different in an operating system. In a simple embedded system, the stack will now be split in several smaller stacks. Every single of those stacks will contain or will be able to contain the context of the specific tasks. As you can see right here, we do have at the bottom of our memory location, we still have our statically allocated data, followed by the heap. But at the top of our memory space, we will have a stack for the operating system itself and the IRQs for interrupts. And then we will have several stacks for our various tasks. That way, as I said, you'll be able to save the context specific to each task in those various stacks. This works for simple embedded operating systems like FreeRTOS, but if we're considering beefier operating systems such as Linux, you will actually have to have specific memory portions for all your tasks, and these specific memory portions will contain the statically allocated data, a heap, and a stack specific for this task. This is what you will have on a regular desktop computer as well, like Linux. When you create a new process, you have your entire encapsulating memory space for that specific process. Let's not look into that. Let's go back to our simple embedded operating system. So, what mechanism can I use to switch tasks? Well, we're going to use a piece of hardware that is our SysTick timer. I did mention that when we looked at interrupt quite some time ago. The SysTick timer, system tick timer is to be used by the operating system to give the general cadence and to have your scheduler taking control over the actually running task. So if I look at what's going to happen, when my SysTick timer will trigger an interrupt, my operating system will actually be looking at what needs to be done. Should I stop my running task and save its context fully and run another task, or should I continue, for instance? Let's go through a detailed example. As you can see on this figure, it is the general representation of your CPU core with your general purpose registers, the status register, program counter, and the stack pointer. What you can see is that the stack pointer is pointing to the stack of task A. The program counter is currently pointing to some instructions for task A, and everything is running like that, and we're happy to see that. We're currently running task A. Just a quick warning here, in this specific example, the stack grows upwards. Remember, for our ARM processor, the stack grows downwards. So now, the SysTick timer fires. What happens? Well, the very same thing that would happen in any single interrupt. You're going to save the actual context and push your program counter onto the stack to be retrieved later on. So in this particular case, the program counter is pushed to the stack of task A, and then we're going to jump into the interrupt service routine. So the various registers are saved as well onto the stack. But then, here's what's going to happen. Now we're jumping into our SysTick timer interrupt, which as a matter of fact is an operating system, the scheduler operating system interrupt. So now you don't want to only have a partial context save for your actual task like you would have in a regular interrupt, but you want to save everything. So you're going to save all the registers, and you're going to save all status and whatnot, even the ones that are not traditionally saved. Once you have that ready, you will be able to save your stack pointer into a fixed memory location inside of the data space. Remember, the data space being at the bottom of the memory space, it's statically allocated, it is not moving. Okay? So you'll be able to save the current value of your stack pointer right inside of the task A stack pointer backup. And now, inside of this data space, you do have all your saved values for your stack pointers for all the tasks. As you can see in blue at the bottom, you have the copy of the task B stack pointer. So what's going to happen next? You're going to now take this task pointer B and save that inside of the actual stack pointer. So now, all of a sudden, you switch the context, because now your stack does not point anymore to task A, to the task A stack, but to the task B stack. And the task B stack does contain the actual context that was saved during the previous cycle where task B was suspended. So now the only thing you will have to do is to do the exact opposite of what you did to save task A, which will be restoring all the registers, restoring the status register, and once you're done with that, now you can finally get out of the interrupt service routine, restore the actual stack pointer of task B, and all of a sudden you are going to point to the task B code with the task B application stack, and you're ready to roll and continue your operation for your task B.